We consider affinity scheduling problems in a multi-typed parallel server system. So as shows in the figure here, task arrivals in the system are of different types and they can be solved by different servers at different rates. Our primary motivation for considering this model comes from the scheduling of requests across servers in the system, in a data center. And in particular, here we consider scheduling of data parallel applications. And for affinity scheduling problem received a lot of attention for quite some time. But the existing work on this problem can be falls into two lines. The one of lines, and for these scheduling problems, we are interested two primary performance metric. One is throughput, and means the algorithm needs to be robust to the load variation. And the other is the delayed optimality. We found that the existing work, some algorithms can achieve these two goals, but need additional information, like requires the arrival rates. And some algorithms does not require the arrival rate information, but cannot achieve the delay minimization. And then how to achieve these two goals simultaneously without the knowledge of arrivals is still an open problem. We would like to see whether we can solve this problem, open problem or not. And it turns out that we solved this open problem in the setting of scheduling for data parallel applications. And for this the data locality is a fundamental problem for data parallel processing, and it means the tasks can be processed by different servers at different rates, depends on the data location. And it turns out we can transfer this problem to a classical affinity scheduling problem. Yeah, and for these affinity scheduling problems, unlike the previous work that only considered of scheduling parts, our idea is to co-design the routing and the scheduling. To design the algorithm, we first need a new queuing structure. Since for our problem, the number of task types is about cubic in the number of servers. For a data center, the number of servers is large. So for instance, for systems with 1,000 servers, the number of task types is about 10 to the power of 9. So that will be huge. So it is impossible to keep one queue per task type. So we designed a new queuing structure. So each server maintains the one queue, and each queue consists of 3 subqueues that receive tasks of different types. That's local, and remote of different that can be solved at different service rates. And the algorithm consists of 2 parts. One is routing. So the routing step actually used a weighted workload algorithms that have the same load as max weights. And the scheduling part is we try to prioritize the service for different types. It always gives priority to tasks that can be solved at a faster rate. And then we showed that our algorithms can achieve these two goals simultaneously. And the key insight is the weighted work routing actually replaces the load of max weight to achieve the throughput optimality. And the prioritizer service help us to achieve the delayed minimization in a heavy traffic regime. And the proof idea flows use the diagonal drift method, but here we cannot apply this method directly, and we need some techniques to separate the system and study the behaviors in different and show the behaviors in different patterns. Yeah. And our future we would like to extend our algorithm for general affinity scheduling problem to see whether we can solve this open problem. I'm Qiaomin Xie from University of Illinois, Urbana-Champaign.